good morning and thanks for joining us this morning for the PID Control webinar. Video is roughly 25 minutes long, and once we finish with the video, we'll go straight into the questions and answers. If you've got any questions, just type them into your question box there in the webinar control panel, and then we'll get to those at the end of the video. So let's get started with the video.
Welcome to today's tutorial. Let's get started. Here's today's agenda. We'll talk about what PID Control is and its tuning methods. We'll talk about how PID is implemented in the Horner OCS product family, and we'll finish with a live Q&A session. Let's talk about PID Control. PID stands for Proportional Integral Derivative. It's a mathematical approach to process control. It was first introduced in the early 1900s by Elmer Sperry. In the early 20s, there was a published analysis of PID control by Nicholas Mineski that grew out of efforts to design automatic steering systems for the US Navy. By the 1940s, PID tuning methods were advanced and were published by John Ziegler and Nathaniel Nichols. Those are still in use today, but have been refined significantly. PID remains the most popular process control algorithm in place. At the heart of it, there are many different forms of equations that are presented in different ways. The two we'll talk about today are their traditional form, called independent form, and the ISA form, known as the ideal form. On the right is an example of a PID block diagram, which has many variations. Don't worry, understanding process control in general is more important than the math. So let's dive into process control in general and how we can use it. What is process control? It's the automated control of a process. It's used extensively in many industries. Examples are listed here. It makes extensive use of analog signals both on the input and output side. With process control, the key process parameters, sensors, and actuators are almost always analog. So we've talked about a process, and now we're adding a process variable, which is the output variable of the process. It's normally held within tight limits. Examples would be temperature, pressure, and flow. As we build this block diagram, let's talk about the example of a pizza oven. Our process is the control of a pizza oven. Our process variable is going to be the temperature of the oven. We also need a control variable, which is the input variable that causes the process to change. Examples would be flow of gas, electric heaters, and the RPM of a motor. If we have an electric pizza oven, our control variable is the output from the electric heater. If it's a gas pizza oven, it would be the flow of gas from a valve. To make this happen, we need a controller to manipulate the control variable in order to maintain the process variable. Our controller is blind to the process variable at the moment. Without the controller having visibility of the process variable, it won't work, so we need to add a feedback loop. When we add a feedback loop, the first thing we're adding is a set point. That's the desired value of the process variable. I'm going to make pizza at 400 degrees Celsius. That's my set point. The error term is the difference between the current value and the set point of our process variable. The controller will return an error if there's a big difference between our set point and our process variable. What are some of the goals for our controller for effective control? We want to get to the set point quickly, accurately, and through a stable process. The importance of each of these goals varies depending on the process. PID brings in the elements that help us accomplish a lot of these goals. The proportional element helps us get to the set point quickly. The integral term helps us get all the way to the set point accurately. And the derivative term helps us avoid overshoot and improve stability. All three are available, depending on the process. I've circled the K terms. Those are the coefficients that will help us balance the proportional, the integral, and the derivative to help us accomplish our goal. Okay, let's go into more detail now on the PID function. The proportional part of the equation has its biggest impact when the error difference is great. For example, I turned on that pizza oven and my temperature was 30. I wanted 400. That error term that appeared when I turned the oven on impacted the proportional term. The integral term acts on how long the error exists. We adjust that integral term enough so that we eliminate any offset error. We have to be careful with integrals. They can create big problems if large errors are allowed to exist over a long period of time, because the integral term just continues to grow. That's called integral windup. The derivative is introduced to handle quick changes in the process. It acts on how quickly the error is changing, so as we approach the set point, it acts as a brake to slow things down. The closer we get to steady state, the effect of the derivative is reduced. There are processes that work well with P control, PID control, or PID control. You won't find processes that use only a combination of I and D. Let's look at what happens as we increase P, I, and D. Let's start with the proportional term. It helps us decrease our rise time, which helps get there quickly. However, if we set it too high, it will increase our overshoot. Increasing it a little bit could help decrease steady state error, but we may struggle to get to our set point accurately. If we go too high with the integral, it will increase overshoot and increase settling time, but it can eliminate steady state error. Our derivative term is there to help us decrease overshoot and settling time. Those are subtleties for many processes. A little bit of overshoot or extra settling time may not matter. In those cases, eliminating the derivative term and going with a PI control may make things simpler. Now let's talk about PID tuning. One thing we want to do before we start tuning is examine our process. Is it a self-regulating process, or is it an integrating process? With a self-regulating process, we're creating a disturbance in the system by increasing our control variable. When we do that, the process variable will settle out. It's the equivalent to me adding a little bit of gas manually to my pizza oven. It'll increase the temperature, which will settle on its own at some time. Whereas if I have an integrating process, and I bump up the control variable and create a disturbance that way, the process variable keeps taking off. Now why is that important? Some integrating processes work well with a P-only control, because they have the I term handled on their own. While the tuning process is similar between the two types of processes, it's not the same. Many auto-tuning products and processes are optimized for self-regulating processes. Before you start the process of tuning, you need to know what type of process you have. Let's talk about the Ziegler-Nichols tuning methods. One of the advantages of the Ziegler-Nichols tuning methods is that they don't require a model, so you can tune a system on a live machine. If you couldn't do that, you'd have to create a mathematical model to simulate that process in order to tune it. The first method that Ziegler-Nichols introduced is a closed-loop method. This method assumes that you've got a self-regulating process because you're putting the process into oscillation to tune it. The process normally requires a chart recorder. You start by disabling your inner derivative terms, enabling the P-only type control, and putting the controller in automatic mode. Then you manually adjust the proportional term in the PID until the process variable is oscillating with a constant amplitude. Then, measure the period of the oscillations and calculate your Kp, Ki, and Kd. Those are the coefficients that you use in your PT instruction as starting points for the control of the process. Those equations are based on a couple factors. They're based on the ultimate gain, which is the value you plugged into that gain constant to achieve constant oscillation. They're also based on the ultimate period, which is the period of those resulting oscillations. Based on those two variables, you can calculate your Kp, Ki, and Kd. Now let's talk about the Ziegler-Nichols open loop method. This is a much safer approach. Tuning doesn't require putting your process into oscillation, and it's done completely in manual mode. Firstly, you put the controller in manual mode, and you record the starting value of your control variable and process variable. The goal is to get the set point or the process variable up to a new level. So you're going to decide on a step change level for your process variable and your control variable. For example, with our pizza oven, it may be 100 degrees on the process variable side. As you instigate that step change in your control variable, you will record how long it takes for the process variable to start reacting. If you look at the chart, you'll see the space between 1 and 2, which is basically the time it took for the process variable to start reacting to the change in the control variable, so we have to record that. Once the process variable starts to move, you're going to be adding more CV. Now you want to record how long it takes for that process variable to reach 63.2% of your targeted step change. So if you're going from, say, 100 degrees to 200 degrees, that's your desired step change. You want to record how long it takes from the time it left 100 degrees to the time it arrives at 163.2 degrees. Then you calculate what the open loop gain is, which is K. We take the magnitude of our process variable step and we divide that by the magnitude of our control variable step, which gives us K. And with those three variables, the TP, the TC, and the K, we can calculate an initial value for our three process parameters. You may want to repeat that experiment a few times to get an average and compare your results. The calculated coefficients are just a starting point. For some processes, they may work and control things beautifully. However, you may need to refine those values depending on how your process is reacting. In many applications, you may not even have a derivative term. Now, there are many applications where auto-tuning or a non-Ziegler-Nichols approach is fine. You might take a completely manual approach or trial and error type approach to tuning your loop. You can do that successfully if you have a good feel for your process. Start out with just your P term. Set your I term and your D term to 0 and start manipulating your KP term. And then come up with a starting point for that proportional term. The value of our control variable is going to be influenced by our proportional term Kp times our error. If you know the output level you'd like to have for a given error amount, you can calculate a starting point for Kp. Once you've come up with a starting point, you refine the proportional control. If your value is too low, it'll take you too long to get to your set point. If your value is too high, it'll overshoot too much. So you'll play with those gain values manually until you're happy with the response and the overshoot of your proportional control. Then you add a small integral factor. When you're happy with the steady state error, you could be done. But if you want to improve settling time, or prevent a little bit of overshoot even more, you may add a small amount of derivative as well. So those are different approaches that you could take for manually tuning your application. So we've talked about PID. Now we'll talk about how PID has been implemented in the OCS family, both in our controllers and in the software. Let's start with the PID instruction that's available in Cscape. We support two PID equations, the independent approach, or the independent equation for PID, and the IRSA, or ideal PID equation. The independent version is a little easier to tune, but in general, they both work well. The PID instruction is available in our advanced ladder and in our IEC package as well. It's an integer-based PID instruction, so all the math we do is done with integer math. As a requirement for the PID instruction, it needs us to assign it 16 words, which can be used for various parameters. They could be an area of consecutive registers for the traditional register-based advanced ladder. They could be based on a structure that consists of 16 words, or an array that consists of 16 words that are assigned to the PID instruction as well. Our PID instruction can perform auto-tuning using the Ziegler-Nichols open loop method. The control variable could be an analog point or a digital point. Okay, so that was the PID instruction. There's a variety of things to configure. We need to assign variables for the variable that handles the 16 words of configuration, or the bank of 16 registers for a traditional register-based approach. We need to assign a variable for setPoint, process variable, and control variable. Then you can manually control your process. You do that by putting the PID instruction in manual mode or manual operation, so we don't typically take away power flow from our PID instruction very frequently. Generally, when it's enabled, we leave it enabled. If we want to manually take over our process, we leave that PID instruction enabled, but we turn on a manual input that allows us to manually manipulate the control variable. To accomplish that, we have to assign a bit which will allow us to go into or out of manual mode. Then we have a couple digital inputs that will allow us to manually manipulate the control variable up or down, but we can also write a new value to the control variable when we're in manual mode as well. Let's talk about the parameters that we set when we auto-tune. So we need to assign some variables. We'll assign a start bit that says we want to start the process, a bit that we monitor which tells us when the process is done. And then we have some other parameters that are not variable based. We can set the auto-tune type. Are we tuning the full PID, or just the PI, or just the P? We can set noise filtering if the process is particularly noisy. We can set the controller response from a pull-down menu to change the speed and accuracy of the process. We can also set a checkbox that allows us to tune at 2/3 of the set. This is an option that you can choose to optimize safety or minimize risk for your process. Okay, so those are the setup parameters. Now let's look at the 16 words that are assigned to the PID instruction itself. I'm showing you in our tag-based ladder with Service Pack 3. We have a PID structure that we've created that you can use in the lower left that allows you to assign a variable using that structure. And then it calls out all the 16 different words that are assigned to the PID instruction. On the right, we've got a table that goes through all 16 of those and effectively describes what they do. So for these variables, we can cover things like sample period and deadbands. We can cover different gain or coefficients for Kp, Ki, and Kd. We can set some biases and some clamps and slew time type settings. And then there are some things towards the end that we don't necessarily want to access or write to those values. Let's go through some of these in more detail. Let's start with the upper and lower clamp. These are the largest and the smallest values of the CV that will actually affect the process. So with our pizza oven example, let's say I set my proportional valve to 80%. That is the maximum amount of gas I'm going to get. If I raise that valve above 80%, the actual flow of gas won't increase. So instead of allowing my ID loop to think that values above 80% accomplish anything, I can set a clamp at 80% of my value. They're important because our PID instruction is not spending any time trying to drive the output to a level that doesn't do anything, which reduces error and will help reduce integral windup. There are other things you can do to deal with integral windup. In addition to clamping your CV, you can zero the integral term when the output is saturated at its clamped value, or when the error and CV are both positive or negative. We want to deal with the CV bias, what is it, and how it can be used. In some processes, the P term on its own might get you pretty close to your set point with just a steady state offset. One approach we can take to solve the steady state offset problem is to add an integral term. But what if it's truly a steady state offset and it's always around the same amount? In that scenario, we can use a bias or an offset to the CV. So for some processes, proportional plus a little bit of CV bias can provide complete control that's acceptable for our process. Now if you're not using a P-only type approach, you're going to set the CV bias variable to 0. Now let's talk about deadbands. There are a certain number of counts above and below the set point within which you tell the PID instruction to stop manipulating the CV. It can prevent unnecessarily turning the CV on and off repeatedly. It's very useful in many applications. Let's talk about minimum slew time. It's a parameter or a variable that limits how fast we allow the control variable to change. We can leave it at 0 or adjust it to a non-zero value. So if we don't want our control variable to change too quickly, we add a non-zero minimum slew time to that variable. So my example here is showing that we set the minimum slew time to 64 seconds. 32,000 counts over 64 seconds means that the CV can't change more than 500 counts per second to maintain that rate. Now let's talk about cycle time PWM. If I've got a mechanical product that has a limited mechanical life that I'm turning on and off, I can make sure that the minimum amount of time that the device is on or off is X seconds to ensure that I don't run out of mechanical life too quickly. It is useful in applications where if I bang the actuator on and off too quickly, it could create mechanical life issues. Now let's talk about the PID tools that are available in Cscape. Cscape has a PID tuning tool, or a PID tuning dialog box that you can utilize. It provides a computer-based user interface where you can make adjustments to your PID algorithm. You can adjust things like your sample period, you can monitor what's happening, you can see the current value of the set point, process variable, and control variable, you can adjust your clamps, all that sort of thing. It's a handy dialog that is used at runtime when you're online with the controller. So how do you instigate that? You start by ensuring you're online with your OCS that's doing the PID control. Go into the program, double click on the PID instruction, and there is a tune button that you can press. Then you get this dialog you see on top. There's also a simple chart recorder or strip recorder available. Those are handy tools when you're monitoring your system manually. Now the OCS also supports auto-tuning utilizing a modified Ziegler-Nichols open loop process to calculate Kp, Kd, and K. So you can see the dialog box there that we set for our auto-tune settings. Is this a full PID? Is this a PI? Or is this a P only? You can adjust noise filtering if you have a noisy process variable. If you want to tune in 2/3 of the set point, you can check that checkbox. So at runtime, after you've already done this configuration and downloaded the program, you can initiate this auto-tune. To initiate this, set the auto-tune variable, which is a bit, to start the process. The OCS will automatically set the control variable to the upper clamp, so it's going to turn that output on full bore. If we haven't set an upper clamp, it's going to be at 32,000. When our CV goes full bore, we're going to be driving the process. Before we started the auto-tune process, we set a set point. You need to have a set point set. The OCS waits to see the process being driven to slightly above the set point. As soon as that happens, the CV is then set all the way down to the lower clamp level. The process is then allowed to fall below the set point. It's not a continuously tuned process, you instigate the auto-tune process. For fine-tuning manually, it's as good as it needs to be. Thank you for attending today's tutorial. The Q&A session will begin shortly.
Okay, so hopefully that gave a good grounding on the PID control using the OCS and how we use the auto-tune facilities and how the auto-tune works. So let's have a look at the questions coming in. Digital output, how do we put the PID controller into the mode where we use a PWM to control or pass on the control variable? Well, in that case, you want to be setting your lower clamp to 0 and your upper clamp to 1. And in that case, the process variable will only move between 0 and 1 to control the output. And then, as we said in the video, you can then use your PWM deadpan to stop high frequency outputs affecting the equipment that you're controlling. So great to do that on an heater, maybe not so good if it's a valve you're opening and closing and you don't want lots of chatter on there. Okay, so that's that. So let's take a look at the upcoming webinars that we've got coming along in the next few weeks. So we've just done the PID Control webinar this morning, August the 12th. Next week we've got logic simulation in IEC, or in enhanced IEC more correctly. We'll be going through all the various debugging facilities, breakpoints, trace points, stepping, and other debugging tools that we can use in enhanced IEC. And then the week after that, we've got the advanced math function blocks. So that's kind of the August schedule. That's already booked in, and that's what we'll be going through. And we'll be spending some time this week working on the schedule for September. So please join us for all of those webinars. So thank you very much for your time this morning, and you can register for all of those webinars by the link seen here on that page. So that's it for today. Thank you for joining, and we hope to see you again next week for the IEC debugging webinar. Thanks very much.